that's like that one.
I'll do 2 in that testing part.
Okay.
I'll do 1 for an application.
Okay, I guess I could do 3.
Who's starting?
I'll do 1 in the start.
So it's general.
All right, this is the redux of the tortoise and the hare story. So, general description, we put tortoise as epoxy, hare as carbon fiber. I think that was, basically self-explanatory, but we do have a short description here. Epoxy is low tensile strength, it's more malleable, and it's damage resistant when combined with a different material. And then carbon fiber, high tensile strength at low diameters, but as we talked about, when it has a higher diameter, it can break due to manufacturing cracks. So yeah, it has a higher chance of breaking. The first story is the basic tortoise and the hare race. The hare initially leads. It has poor performance with the rigidity of the fibers, and it's more weak for concentrated stresses when we're talking about carbon fiber, because the epoxy has stronger endurance, as we see with the tortoise eventually passing the hare. Epoxy is much easier and cheaper to manufacture, and a lot of people would say that would mean that it's a worse material, but in this case, it's not, right, for a specific application. So, yeah.
And so when we kind of adjusted the story this time, we talked about the hare, analyzing the mistakes and learning from them. And we talked about using different sort of manufacturing techniques in order to improve the performance and kind of metrics of the material. And so one of the common manufacturing techniques using carbon fiber is weaving. So instead of using unidirectional carbon fibers, when you introduce the weave, so you have both directions of stress resistance, it makes it much stronger and improves the performance. And so this was kind of an interesting example of something I'd done in one of my previous classes where we used unidirectional carbon fiber. And so because the carbon fibers were facing this way, and so when you would put it in, and we put it in tension, pulling it apart, you found that every single time it wouldn't crack in the middle like you'd expect from a dog bone. It'd always shear here because the unidirectional is wanting to shear up in the fibers like this, versus if you were to use a woven carbon fiber, you would prevent that since you have the fibers going in both directions. And so we said that this time, when the tortoise agreed to another race, this time the hare won the race due to these improvements in the design. And so with something like a woven carbon fiber, you have a high strength to weight ratio and the stiffness of the carbon, as well as a much reduced volume and weight compared to epoxy. And so usually when you make these carbon fiber layups, you use something like a 40% mass ratio. And so you want to have, with this one, you found you want to have more of the fibers and less of the epoxy, because as you added too much, more and more epoxy, something like if you were adding 80% epoxy, 20% carbon, then you had so much epoxy that actually made it more brittle and had much worse performance. And so this having the more of the carbon and less of the epoxy helped not only make it stronger, but also you're thinking about applications like aircraft where you want to reduce weight, then having less weight and less volume is pretty crucial as well.
So for the third one, Tortoise wins again because Tortoise analyzes the previous loss. Because, for example, still if we test in transverse directions, we know that fibers don't perform well, and in compression tests, basically the fiber will just buckle. So epoxy, because of the uniform load distributions, it will perform better, and it will not fail. Also, epoxy is waterproof and can relatively float and cross the river in that way, as tortoise can cross the river. While fibers, they swell up in water. Carbon fiber swells up in water and also is more prone to breaking and is limited in swimming. And hence, tortoise caught up to hare and overtook him. So the ability of epoxy to be waterproof and perform well in water allowed it to win.
Next up is the part where they team up to cross both the river and the overall raise. And so when we combine carbon fiber with epoxy, we obviously make carbon fiber reinforced polymer, where the polymer here is the epoxy. And so in the first half of the race, the Hare will basically carry the team by having its increased tensile strength, as we mentioned before, and also the design flexibility. It's like, say the path was more curvy, you can always like adapt to whatever specific application. As we mentioned, we can weave the fiber together, but we can also, since with the overall composite, we can mold it into different shapes. We have an example of this on the bottom right, of just molding into a particular shape, and that also will allow you to make more complex shapes as well as save cost overall. And so in the second half, as we mentioned, the tortoise or the epoxy is waterproof, so it helps with that. But it's also resistant to damage, other environmental damage, such as corrosion, and it also provides insulation, both thermal and electrical. And it's also ductile, so it'll slow crack propagation. So together they'll finish the race. And overall, as we mentioned, it'll save not only cost, but it'll also save weight. And so this leads to improved fuel efficiency. And so for overall, like real world applications, what we can take away from this is that it's used in aviation, as we mentioned in our previous slideshow, where we talked about all the different composites and they're used in like aircraft and other planes. And as we mentioned, this is for weight reduction, design flexibility, where they can mold it and make complex shapes, as well as provide the thermal, corrosion, and other electrical resistance. And we can see these in different composites such as Kevlar, fiberglass reinforced polymers, and ENS glass. It's also used in different applications other than aircraft, such as we mentioned boating, automobiles, and different sports like tennis and biking.
This was just an extra slide I thought to add, kind of related to that testing I talked about. So when we talk about making the carbon fiber reinforced polymers, also matters, like we talk about their strengths and weaknesses, and so like I mentioned in the previous slides, it matters how much epoxy and how much carbon fiber you use. And so you can see this was, on the left was 20% by mass, this was 40% by mass, and this was 30% by mass. And so you can see that the one that had the highest performance we found was this 40%. And so like with this 20% one, you had much higher levels of stress. And same thing this one here, where you saw much higher levels of stress. And so we found that there was kind of a perfect ratio. If you use too little fiber to epoxy, if you use too much fiber to epoxy, either way, like they didn't work well enough together that you saw decreased performance. And so while they're still pretty strong, we found like across all the different mixtures, it could withstand a stress of like many tons of force. And so I mean, either way, it's still really strong, but we found like much increased performance since 40%, which when we did research also found that it seems to be kind of a very common mixture ratio that's used kind of across applications, like across industries.
Okay. Yeah, wonderful. So going from your previous analogy with the reinforced concrete to this, what are the primary differences that you see? Because the story is the same, the storyline which you're comparing. That's a civil engineering application, there's an aerospace engineering application, but are there certain intricacies with this which you didn't probably perceive in that case?
Like we
concrete.
talked about before, like concrete's very cheap and steel's very cheap, and so just cheap and also simple. So like it's pretty simple to make like reinforced concrete, and so that's why it's used so widely without civil engineering. So like it's cheap and it's like easy to build, and you can make it quickly, versus carbon fiber layups and composites are not just more expensive to make, but they're just more complicated, like more time consuming to manufacture, which is why like we don't make roads out of carbon, because if you don't need, like it has better performance, better characteristics, but if you don't need that, like in an example like a bridge or something, then there's not necessarily that benefit to use it.
Okay.
Yeah, and also that concrete is very heavy but cheap, so it can be used on the ground because we don't care about weight, but for aircraft we really do care about weight. And so yeah, we want to minimize the heavy materials that don't necessarily have that great of a property. While on the ground, we don't mind just using more, but costing less overall.
I think with steel and concrete, I think it's more important for it to bear a load, and that's its main purpose. As with this example, this is like more, you need more things like, high thermal resistance, high chemical resistance. It's used for properties where, it's not used as much, right? Like steel and concrete is used throughout the building. It's like everywhere, but this is used very specifically and sparingly, so that all those little properties matter more, and they're more important in use. Right?
So it's like Anai mentioned, where we talked about how the concrete and the rebar were mainly used for like structural components, whereas this has more exotic uses, as we mentioned, with the aviation, the automobile, and the sporting goods. But in both cases, basically the tortoise represented basically damage resistance for both cases, where it was the concrete prevented against corrosion and other kinds of stuff, while we had a similar thing with the epoxy, protecting against the environment. And then the same thing applied where like the fiber kind of represented like the muscle fiber of the rabbit, where we had the rebar represent that, and we also had the carbon fiber represent that, where it's like more stiffness. But I think in this case, the carbon fiber is more vulnerable to like loads, as long as it's not in that same uniaxial direction. So like that's the main difference, where it's weak in that regard.
So also just to go back to that slide where you were talking about those graphs, this one. It's very interesting thing you brought up, because if you look at the equations that we had for micromechanics, it said that it's a fiber volume fraction times the fiber property plus the matrix volume fraction plus times the matrix property in the case of the Young's modulus, for example, along the fiber direction, right? And that's something that you've been working on related to your homework as well. So the higher the volume fraction of the fiber, it's supposed to keep on increasing, right? According to that. But there is a practicality over here, which is where I liked your title there, real life, because there is something which comes purely from the theory and the math, and there is something that comes in terms of the actual restriction. So what do you think really happens when you keep on when the fiber volume fraction is really low and you start increasing? You do see a huge advantage, but you're saying there's an optimum that is reached and then it falls down. So what do you think would be the reasons from the fiber and matrix point of view, from the little bit of micromechanics that you have learned, which makes it deteriorate after a while?
I mean, a lot of it, even not even micromechanics, some of it just came down to like we found like manufacturing problems. Like so, if you're using really low volume fractions of epoxy, manufacturing-wise, it's harder to get proper like absorption and saturation of the fibers. And so we found like every time I go to crack, there's always like some sort of bubble or like something weird that happened where it would crack or shear at that spot. And so the more epoxy you add, it's easier to prevent that and just totally saturate everything out. But the more you added, it seemed like the weight started to become a problem on itself, where there's just so much epoxy and like not as much fibers that the epoxy properties started to take over from the carbon properties. And of course, epoxy is not going to hold a load as well as the carbon fiber does.
Okay. So there's also a theoretical limit on how much you can go with the fiber volume fraction, as long as you want to maintain that continuity. See, there's a possibility you just have fibers, which you don't have matrix at all, that's 100%, okay? But you'll obviously have gaps depending upon the geometry of the fiber, which is typically circular. So when you bring many circular fiber cross sections together, you're not going to fill the space fully. There are going to be gaps in between them, right? So the whole idea is that once you go beyond a certain point, there's going to be agglomeration. So the bunch of fibers together. And remember, we talked about when a fiber breaks, there's a matrix which does the stress transfer. So that stress transfer starts suffering, which is why you see in real life testing, you will see that beyond a certain point after a volume fraction, even if it does not actually approach the theoretical maximum, because you can actually draw, let's say you draw a set of 4 fibers touching each other, and then you draw a square around that. You can actually say, based on the geometry, you can actually find out how much is the maximum fiber volume fraction that you can have. But you rarely would go even close to that, leave alone reach that, because once the fibers start touching each other, the stress transfer, which was so beautifully done by the matrix, is no longer done. But let's take a step back and look at, see, you talked about the huge advantages that are there for the teamwork, okay, which is what we wanted to get into, because you look at most of the civil engineering constructions, they are reinforced concrete. Most of the aerospace constructions these days are all the fiber reinforced composites. But there are some takeaways even from the first 3 episodes of the story, where individuals thrive, right? So teamwork thriving is the big takeaway for us. But there are possibilities when there is no team. It's like individual sports and team sports, right? So there are certain places where individuals are necessary and you thrive there. So based on any one of those 3 episodes, can you think of applications in aerospace where, let's say, just the epoxy is used or just the fiber can be used? So therefore, you essentially leverage the strengths of that, because the strengths of the other is not required in particular specific applications, which are not very common, but there are a few like that. So can you just probably think about possibilities like that?
Just one quick thing, I can let someone else join in too, but maybe not like epoxy and carbon fibers. I mean, you wouldn't usually use like dry carbon or just use epoxy, especially in aerospace applications. But if you go, can you go back to the one with the plane on it?
Maybe if I
like
give
you
you
use
a
like different materials, and like we said, like, you know, most of this plane is made of composites, like 50%, but you're still using like aluminum here on the leading edge of the wings, and you're using like
that's a totally different material. So what I'm saying is the constituents of the composite. So let's say the composite is carbon epoxy, right? So are there places probably we can use carbon alone or epoxy alone? Because that's the analogy with the first 3 episodes of the Hare and Tortoise story. To take you back to your first presentation where you talked about reinforced concrete, you can think of, let's say, the Eiffel Tower doesn't have any concrete, it has only steel, right? So it's a situation where can we have only fibers, not the matrix? And similarly, there are some applications where you can just use concrete by itself without the steel reinforcement, okay? You see that quite a lot applied on, let's say, floor rings and things like that, where you just don't need that level of strength and stiffness.
Yeah, so one example would be like if carbon fiber is used in a very thin, like very small, as we talked about in that one class where the diameter is very small, maybe it's not necessary for the epoxy to cover up those cracks when they show up when you have higher diameters, right? So when you use carbon fiber for very, in applications where it can be used with a small diameter, you might not need epoxy as much because those cracks are less likely to show up.
And for the epoxy, we mentioned that it is for damage protection, and instead of having it as a composite where it's like a part of the matrix, you can just have it as like a sealant just to cover something. Right. And so you mentioned that specifically with like the floor, so you would use that in like the inner cabin where it's more of like an aesthetic use, and also to protect against like damage aware from people coming in and off. And so you'd also use that to cover anything else that you wanted to protect really from outside.
I think specifically for carbon, I think it's kind of tough because you usually have to put carbon in a matrix for it to like have a proper use. But if you look at other composites, like ceramic composites are used very widely on there, and it's not necessarily, it's just like the ceramic on its own, especially like in space flight where we talked about, even one of our previous, I think, presentations, we talked about the helicopter, the aircraft, and the launch vehicle where ceramic composites have very high thermal resistance, and so like in that very specific use, you would just use that ceramic composite for that use. You wouldn't necessarily make it like a reinforced composite in that sense.
So I guess just for specific carbon fiber, when you need to just lift heavy loads, for example, on a crane, potentially, you can just use carbon fiber instead of like regular, whatever they're using, like steel cables. You could use carbon fiber since it's primarily just tension. You're just lifting heavy loads, putting heavy loads down.
Yes, that's the key. So if you know what it's good at and what it's really bad at, situations where that what it's bad at are not encountered at all, you can completely rule it out without a doubt, then it is a possibility. Yeah.
Yeah.
You can also use like epoxy as like just an insulator. Like if you want to insulate something, right? Just heat or just any sort of insulation. Epoxy would be a great use for that. Yeah.
Those are excellent responses. Matt, you talked about going from episode 1 to episode 2. One of the things is improving the manufacturing processes, and you gave weaving as an example of that. So that's a very interesting way of looking at it. And in fact, we talked in the class about woven Kevlar, for example, being used as an impact energy absorption in engine containments. Okay, so whereas most of the older containment structures have been made out of metals, as I've been telling you, there's a blade out. The blade should not get out of the engine because that's much more disastrous. It should be contained. That's why it's called the containment. And so those containments were traditionally made out of the metals, which is essentially rigid and solid. But of course, it has a flexibility because of which it absorbs the energy. But now with weaves, like you're talking about, a woven fabric of Kevlar can absorb a lot of energy. So you don't need epoxy. In fact, if you have epoxy, it makes it brittle, and therefore it's rather not being there is actually more advantageous. Okay, so that's another example. And it's good that you talked about the non-structural applications of epoxy. I think that's where it goes towards. Even in structural applications, you can use it as a glue. So essentially, when you're trying to put things together, adhesive bonding, which is gradually replacing some of the traditional bondings like rivets and bolts, or maybe used in conjunction along with riveting and bolting. You use adhesive bonding as well to ensure a greater bond strength. So those are places where, again, without the fiber, you're using just the matrix or epoxy alone.
All right. Should we move on to the next slide?
You had any questions, Prashant? No.
Okay, so for the next one, we're talking about composite fibers. We're going to start off with the derivations first, and then we'll end up talking about the composites, the actual fibers later.
Mm-hmm.
So first, we're deriving Poisson's ratio. So I've set up the coordinate system on the top, where the x1 one direction is to the right, the x2 two direction is to the basically upwards. And you can see the drawing of basically the layers that we're using.
What do you mean by x11? Why two subscripts for that?
So this is on like it's on the one cut, and it would be pointing in the one direction.
Just x1 and x2.
Yeah.
Yeah. So you have to be really little
X1,
careful.
X2.
Yeah.
Okay.
Because see, x1, x2 are determining the position, right? So the position is like a vector, a position vector, and a vector is a first order tensor, so it should have only one subscript. Okay.
So then it should be x1 this way, x2
Okay.
this way. And so then when we're talking about these, we're talking about the two layers, and we only have one uniaxial stress here, which is acting in the one direction. This is the one cut in the one direction. So to start off, we're going to assume that there's perfect bonding between the two layers of both the matrix and the fiber. So what this means is there's no gaps. So the change in length in the longitudinal direction will be the same for the overall composite as well as for the matrix and for the fiber. And so when we apply a force, this stress will cause a strain where there's a change in length. And so that's the definition of a strain, where it's change in length over the original length. And since we assume perfect bonding, that means that the strain caused by this force is going to be the same in the longitudinal direction for the fiber, the matrix, and the overall composite. And we're treating the composite as this idealized homogeneous model that's not really in existence. We're using it so that we can basically model the situation. So next up, we're going to talk about, we talked about how the force will cause a strain in the longitudinal direction, but because of Poisson's ratio, a strain in the one direction will cause a strain in the other direction. So we have that in the bottom left, where you see basically the definition of Poisson's ratio, where we have the strain going on, the input coming in first is the longitudinal strain, and the output will be the transverse one, which is in the 2-2, is in the 2 direction. And so because of this, we know that there's going to be a change in the thickness of the overall material. And so because we're going transversely, we can't do the same assumption before where we mentioned that perfect bonding, so the strains are the same for each one. So since that's not the case, but we do know that the overall composite is made out of the fiber and the matrix. So the change in thickness for the composite is going to be the sum of the change for the fiber and for the matrix. And we're also assuming here that there's no additives or defects, so we can assume that that summation holds true. So there won't be any gaps or anything. And so knowing that, we can go back to the definition of strain, where it's the change in thickness, or change in length over the original length, where this is we're using the change in thickness over the thickness. So knowing that, we can plug in, we can solve for the change in thickness and plug into our equation before, and we can solve out, so we have this equation. And then knowing that, we can divide out by the thickness to get a volume fraction, where we know that all the other dimensions are going to be the same. So the length is the same, and then I guess the breadth is also the same. And we're assuming this because, as we mentioned before, that it's an idealized homogeneous material without any additives or defects, so the dimensions are going to be the same. And then following that, we can plug in for Poisson's ratio, where we're basically subbing in the different ratios where we have the same. We're solving in for the strains, and we're pulling that out. And then we mentioned before that these were all equal, so we can also cancel them out. And since we're assuming that the matrix and the idealized composite is isotropic, we can get rid of some of the subscripts. So for any directions for the longitudinal or transverse matrix, they go away. So we're left with the final solution.
Yeah. So that 1122 is continuing with your nu as well. So nu, remember, is just a second order
It should just be nu
quantity.
1.
So
2.
yeah, so just 1, 2, right?
Okay.
So because you introduce 1122 there in all your news also, it's becoming 4 subscripts. It's not necessarily just 2 is enough. And that might sound like a very simple, innocuous error, but in terms of the math involved, it can become entirely different problems. So just be a little careful about that. What's the last thing you mentioned in terms of the assumption, isotropic? Or,
it's isotropic mainly for the matrix and for the composite. So that's why we're able to get rid of
the composite?
For the idealized composite. Well, only for the matrix in
only
this
for
case.
The matrix, yeah.
But we're
neither
doing
for the fiber nor the composite. So it's only for the matrix, yeah.
Some other assumptions that I included were, since the overall equations required Hooke's law in general to derive Poisson's ratio, I included that we're using a linear and elastic model here, and there's a uniform distribution of both the fiber and the force. Okay.
I'm glad you did it handwritten. It looked much more presentable. Your handwriting, of course, much better than mine.
Yeah, so now we go to the shear modulus derivation. So we again assume homogeneous, uniform, and perfectly elastic material, and that follows the Hooke's law for the shear modulus equation. So the general shear modulus equation is the shear stress over the shear strain. So since we have basically kind of materials in parallel, it's isostress. So all the forces and hence the stresses will be the same, since the area of application is the same as well. So by rearranging the initial equations of shear modulus, we can put the shear strain as shear stress over the shear modulus, and also shear strain is the angle by which the material shifts, and we know from Pythagoras that tan theta will be the distance by which it moved at the top divided by the thickness of the layer, but we can assume that theta is small, so tan theta is the same as just theta, So we can equate the shear strain to delta L over T. Also, as we can see that the difference in length of matrix and fiber combined are the same as the total difference in the composite, and hence and we can rearrange the gamma for difference in length. So the difference in length is the same as gamma times thickness, and so if we substitute this equation into this formula, you can get that the gamma of composite times thickness of composite is the same as gamma of fiber times thickness of fiber plus gamma of matrix times thickness of matrix. Then we can substitute the equation from the shear modulus, so we get that shear stresses over shear modulus. Just shear stress over shear modulus replaces the shear strain. Then we know, since it's isostress situation, we can cancel out all the stresses in that equation. Then we can divide everything by the total thickness of the composite. So on the other side, we get the thickness of individual material of the individual component divided by total thickness. Then, since the overall length doesn't change that much, and the third dimension also stays the same, if we multiply the fractions by length in the third dimension, we can get the volume of fiber and matrix divided by the total volume, which is the same as the volume fractions. So we get the following equation. And finally, we derive the common denominator. So we multiply fraction of fiber by the shear modulus of matrix, and similarly we do with the volume fraction of matrix and shear modulus of fiber. And so we get this equation, which is basically the flipped version of the final equation. So we just basically flip it since it's two fractions, and we get the final equation. And here, so we know it's similar as in the previous slide, that x1 goes in the longitudinal direction and x2 goes in the transverse direction. So they're interchangeable, 1, 2, and LT. Yeah.
Between the two of you, you've looked at the Poisson's ratio and the shear modulus, right? Derivations for the composite in terms of those for the fiber and the matrix. In terms of the assumptions involved, are there any assumptions which are present in one but not the other?
I guess small theta. Well, also I guess one is isostress, one is isostrain. That's kind of an assumption as well.
Yeah.
I think that was
Yeah.
Yeah. Okay. Prashant, do you have any questions on either of the derivations?
So this is finding top 5 fibers for buckling, strength, and stiffness when using an aluminum and epoxy matrix. So the goal is to find the strength, stiffness, and buckling design values, which are the 3 main values we talked about in class. And we're using these equations here. The commonalities in these equations is the modulus, the elastic modulus, the density, and then the ultimate tensile strength. So we have to find those 3 values. UTS and density are found online. That's not that big of a deal. The Young's modulus needs to be calculated, right? So that is a separate equation that we need to do. We use the rule of mixtures. So this is what we're looking for. We have to use the fiber's elastic modulus and then the volume fraction and then the matrix elastic modulus, and then its volume fraction. So finding all these values, the materials elastic modulus is found online. That's where we found the UTS and the density as well. That's where we found it online. The matrix volume fraction is 0.4, which you gave us in the slide. And then finding the fiber volume fraction was just subtracting by 1, so you get 0.6. And then these values were given to us, the aluminum matrix 71, and then epoxy is 3.4 gigapascals. And then we just put this equation into a spreadsheet and used it multiple times.
So first, for the aluminum matrix,
Any significance of that picture there?
who added that picture? We want to start kind of introducing, we talk about there's aluminum matrix composites as well as the epoxy matrix composites, and why there's differences between those, and why only certain fibers can be used in the specific matrices. And so for aluminum in particular, you see vastly different kind of fibers are usually a lot stronger. And different, we'll kind of see as we go through what the different fibers are made of. So we kind of picked 4 big factors that go into the compatibility whether or not a fiber can work with the aluminum matrix. So of course, with either of these, that has to have good adhesion. So the fiber must be able to adhere to the aluminum or aluminum alloys that are used in the matrix. Otherwise, you're not going to have a combined matrix. You have to minimize any sort of stresses that would occur during thermal cycling, because if there is expansion of the aluminum or of the fibers, that can lead to delamination of the two, and so again, you would no longer really have a matrix. As well as something unique to the aluminum matrices are that in the manufacturing and processing techniques, you're going to use much higher temperatures that are needed to manufacture metals. And so if the fibers themselves can't withstand those temperatures, then that's going to be a problem. Even if they get to work in their uses, if they can't be manufactured together, then that's a problem from square one. And then of course, the fiber should not promote any sort of corrosion in aluminum, because of course, long term that would really deteriorate the condition and kind of usability of the material. So first, again, aluminum buckling design. We kind of have this spreadsheet that's kind of a mess. So we have 5 different fibers, and so they're all made of different core materials. And so we saw that this one was reinforced aluminum fibers with, I think this one was maybe Kevlar. This one was the Safil fibers. That was a very unique kind of fiber that's kind of different from most other fibers we looked at. And this one was, we had a whole list somewhere, I think later in the presentation, where that one was a, what was the name of that one fiber? It was a boron, I think it was a boron fiber, that one. And so it's again kind of a different, where usually we talk about carbon fibers as being kind of a main one, or glass fibers, but using these kind of boron fibers and Kevlar fibers is kind of unique, and we wanted to look at those in terms of how they are different. And so we picked these because of their compatibility with aluminum, as well as their properties and kind of metrics between all of them. So the one highlighted in green was this thermal ceramics bulk fiber. And so when we go to the next slide, we made this plot that plotted all the materials in the x-axis versus we left it unitless, since each of the buckling, stiffness, and strength all have different units. And so these are all just their unitless values. And so you can kind of compare against each other how they compare in terms of is one better in certain cases and why there's a better in other cases. So you can see if we're looking at the buckling or across so if we start with buckling, you can see the buckling stays, when you see this across all of them, the buckling stays fairly consistent. And so between these two materials, the buckling is the highest, and then you also see that again their stiffness is the highest and relatively similar. One odd thing we found across these is for some of the strength design, tends to be outliers. We think the reason for that is because when we did the research, we took the values to calculate these values from the manufacturer's handbooks. But across manufacturer's handbook, they gave different sort of definitions of the ultimate tensile strength. And so that was kind of the one value that seemed to vary quite considerably across the handbooks. And so while the others to be pretty consistent since the strength design was the only one that took into account the UTS value. We think that kind of threw some of these values off.
I think the main thing is that they could have switched it for, they could have said ultimate tensile strength and meant just tensile strength. They could have meant like just tensile strength, and that's really where we think these outliers came from, is that the difference between tensile strength and ultimate tensile strength is what is recorded, and why there's outliers.
And so,
Also, I would rather suggest instead of saying buckling, you would say stability, because that's a desired feature, whereas buckling is an undesired feature. It's like saying instead of stiffness, flexibility, or instead of strength, weakness.
Okay.
So just being consistent with all three would be good. So
that makes sense. Then for the strength design, strength design was where we really saw Kevlar kind of stood out as the strongest consistently, since that's kind of what it's
so the previous slide had all these outputs as well.
So these are different. We found 5 different materials for each. So like for the strength design, we found materials. When you calculate all the values, you still see like is it still have these other properties as well. But again, we saw that for the strength design, these fibers are the best, and so we see. There were ceramic fibers, but also again, this one that stood out the most was the Xylon fiber that had very high strength. So you can see that here, where with that strength design in the blue, we tend to see much higher values than we saw before. Again, for some reason, there's these 2 outliers, and whether or not that comes from that really being the strongest material, that comes from differences in how they reported their all-time tensile strength, is a little bit more unclear. But also cross-line, so even when it has these stronger materials, they also have much better stiffness as well, which kind of going to make sense when you think about Kevlar or other materials that are going to be used in high-strength applications. Again, their stability design tends to be a lot lower. But the reason why we kind of picked this Xylon fiber as being the best is because it kind of by far, kind of close to the hexyl, but still kind of by far the highest stability design, as well as having comparable stiffness and also very high strength. But again, this hexyl hexatone fiber as well also kind of was pretty comparable versus some of these other ones like the 3M hexyl fiber, which kind of had a lot lower kind of performance characteristics. And then for stiffness design, again, we see a lot of times the kind of product lines repeat. So we see these 3M Nextel a lot because 3M's Nextel line has a ton of different fibers that are all kind of designed differently for different use cases. So again, we see like in this one we had the 3M Nextel 720 and the 3M Nextel CFAMMC, which was, I don't remember the acronym, but it's composite fiber aramid. So that was an aramid fibers, which that kind of went along with that Kevlar. That those 2 kind of stood out as being consistent. Like any fibers that are made of those materials were typically had really good characteristics. They were usually more expensive and kind of heavier, but had this, like if you were just wanted the strongest material, that was one to go for. And so again, on the graphs, you can see, again, we kind of have the same thing where the stability design, and that's just like kind of characters of that's what this value is, like the buckling or the stability design is a lower value compared to these other values are higher. So again, looking at this Toray Industries Torica fiber, it has, again, we kind of looked at, if we're looking at stiffness design, we wanted the highest value we could find of stiffness, which was here, but also looking at this fiber, it not only had the best stiffness, it also had the best stability and high strength. Which again might have been an outlier, but it was at least like, versus like this material on fiber had like very, very low strength. And so that was kind of a downside on top of having like low strength and relatively low stiffness. That wasn't like an ideal fiber to use, even though like, it still would work in the aluminum matrix, and so overall is better than other fibers that would have very, very low performance, but in comparison some of these other materials just didn't stand out quite as much.
Okay, so now we're talking about the epoxy matrix. One thing I wanted to mention before we start was that like the way we picked our materials, you know how you said you wanted to be like the next, like the highest?
Yes.
The way we did it was like, hey, is it still currently being sold? Right? So if it's being sold, that means there's no newer one coming up, right? So if it's being currently sold, that was our cutoff. It's like, okay, we're gonna use that. We're gonna use that as data, right?
I haven't gone over this slide.
Well, not necessarily, because the one that is being sold might be economically viable,
Right.
whereas there might be something newer discovered which is better in performance.
Right. Yeah.
But
it's
for
higher.
different markets, you might
Yeah.
continue to retain some of the older
Sure.
older models
Yeah,
as well.
but I think that was one of our main determining factors was like, is being crumbles. So for compatibility with epoxy fiber, we talked about adhesion in the last presentation, right? Is that, you know, it can be used for adhesion. It's also in the chemical process of how it's being made. Good wettability was a big one. You know, making like how water spreads on the surface. High chemical resistance. We could also talk about insulation as a, you know, kind of a factor as well. Thermal properties, and then environmental resistance, like environmental factors like the air or anything like that, like moisture, right? Like water, for example. So. And then low cost is a major benefit when compared to metals. So for the buckling design, we found that it was this Torre material. And then you'll see a lot of these brands like, you know, keep repeating, like Ube, next, like the 3M Nextel, Torre was another one that kept being repeated. And a lot of the data we sourced from similar sources because of that. So here we see kind of an increase in strength, and this is one where I'm kind of like, hey, this might not just be an outlier or a data error. We can kind of see this increase, and then so epoxy strength design. Here it's one of the Hexel brands, so they have like IM1, IM2, like each of them have a very specific. That doesn't mean that like IM7 is better than IM6. It's just where it's used. You know, that's basically all that is. This is another graph of that. Stiffness. The DuPont Kevlar, so that's really interesting. Is that it's Kevlar for stiffness, right? So when we're Kevlar for stiffness, that's kind of that's it. That's our presentation.
Like I had mentioned too, you see this again with the epoxy matrix where these ones that had high stiffness values also had very, very high strength values. Again, this definitely isn't an outlier since we consistently see these three are very high strength values. Again, like I mentioned before, you kind of tend to see more unique materials that aren't like as simple or like as economical because you're just going for like as much strength as you can have. So you see this Kevlar, or you see the aramid fibers, you see this basalt fiber. They're like very kind of obscure materials that. Again, we see carbon fiber, we see glass fiber a lot, or even like you saw like in the previous presentation last year, they were looking at like bamboo fibers that are very, very simple, but they're not going to give you, like, if you just want like as much strength as possible, you're not going to get that from some of those simpler fibers. And one thing too that we looked at, kind of he talked about in terms of how we source these, there were some fibers that might have been higher performing, but they were so new and like advanced. We saw one that was like a braided carbon fiber rope from like one of the universities in Beijing, but it's so like new and experimental that there's not like a manufacturer's handbook on like and knowing anything about the specifications of it.
A lot of times they don't want to give the data out yet because it's just like cutting edge and they want to patent it and stuff like that. So that's why these are more readily available.
These are done? Yeah. We're quite impressed by the selection that you have because you've gone into actually, I think MatWeb is a great resource for a lot of these material properties. Apart from the company websites also, sometimes they have these specifications, so you typically tend to get that in as well. I also like the kind of color coding that you have. I think you took from one of the previous feedbacks. It makes it much more clear. One more thing I would like to see probably in your future presentations, probably not for this course but for anything else, is whenever you put numbers, there has to be some units going with it, and since there are 3 different units there, instead of putting it on the axis, you could probably put it in the bracket, which you anyway presented from the screenshot from the homework itself, problem definition. But if you can just put that in the brackets, and as I mentioned, the buckling as well, instead of that, just mention stability. Yeah.
That makes sense.
One more thing, at least from Matt, I expected a little more dramatism, more like, see, because these are like our superheroes, our structural engineers. These fibers, the cutting edge fibers, are like our superheroes. So maybe the same slide, instead of just putting it as a slide, maybe bring in an animation. First come with just these names without all those dots. It's like Grammy style or maybe Oscar style. Then the nominees are, and then the winner is. so something like that to make it a little more engaging. Okay, so overall, I think it's a great selection. You have any comments on any of these fibers? Yeah.
Just curious. Which manufacturing method they are using for fabrication of that aluminum fibers composites?
No, the aluminium is a matrix for them. So they have 2 choices of matrix, aluminium and epoxy. The rest are all, what they have chosen are all the fibers.
Which manufacturing?
There was one that mentioned there's like aluminum in the material itself. We didn't like go in depth research like each of these like exactly how they're made, but there was this one. This one is touchstone. I think it's like impregnated with aluminum in it, and that's where this comes from. I don't think it's like aluminum fibers itself. Like I could like always talk about the next. That's like we didn't like, cause since there's 30 of them, we didn't like look exactly like what each one were, as opposed to more of just their performance characteristics. But
I think this one is more just reinforced with aluminum rather than like I mean, it's in the name. It's
Sure.
reinforced.
Right.
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 So we didn't really go into detail on like the manufacturing process for every single material, so I wouldn't.
I mean, that's fair enough,
feel
because that was not
comfortable.
part of the question, but Prashant has an important point. Those of us who are interested in a little more details of this, we really like to know what aspect of the manufacturing process made it so strong or so stiff or so stable. So maybe for other fibers, maybe can we adopt a similar kind of manufacturing nuance.
So different manufacturing process, they give the different strength for that composite.
Absolutely, that makes perfect. Yeah, and I'm sure all of these have different manufacturing processes. A lot of them are, bespoke to the company as well. Like some of them would not be willing to tell us.
See, it's just like with alloys, right? So it's a question of what metals you're combining in what percentage, and also the heat treatment process, which is a part of the manufacturing. Same here also. Apart from the manufacturing which Prashant mentioned, it's also what we call as the precursor. So the precursor is what you start off as the raw material in order to make the fiber. So one is how the process of manufacturing is, but what you start off as the precursor. So for example, it could be PAN. PAN is called polyacrylonitrile. If you start with that, you get some level of stiffness and strength. If you start with some other precursor, you get the opposite way. So depending upon whether stability is a more important criteria, stability and stiffness on the one hand, which are dependent on E, and strength is the other criteria. So depending on that, you tend to choose one precursor over the other, one manufacturing process over the other.
I think one also important thing is like, for example, like if we were looking at food, right? It has the ingredients list on the back, but they don't tell you how it's made, right? But that's because it's proprietary. They don't want to tell you how things are made. So either, like KFC would be like, oh, this is a specific blend, but they're not going to tell you the percentages because then you can just make it at home. So that's the kind of thing. Like I would say for this is like they may give you the materials and not give you the process, or give you, hey, this is the basic level process, but not give you any more details on how specifically why these materials are different. You know what I'm saying? So.
So it's a very valid point, the proprietary nature of some of these cutting edge materials. So the source for such things, rather than go through the web or even let's say the journal papers, is to go for patents. So if you look at patents of these companies, so typically they will have more information, because once the patent is granted, they're willing to, because anyway their intellectual property is protected, so they will share some of that proprietary information in terms of the manufacturing. There are, in each country there's a patent office. Like Indian Patent Office, there's a US Patent Office called USPO. They have their own portal in which it's not open to typically the Google kind of search. So if you go to the USPO website, there is a search engine there. So you can search through that and get some of the patents.
I think I've
So
done that
that's
before, but many years ago.
right,
So,
right.
That's
Right.
a good way of
So that's one thing you talked about, so which is especially for the industry. If the industry is making it, like most of these are commercially available, which you talked about, Torre, Hercules, and all those. But as you also, another important thing you mentioned is academic labs, like Chinese labs or something that you mentioned. So they are more keen on sharing the information. Of course, they are also interested in patenting and things like that, we in academia, but at the same time, if we think that that's going to be a long drawn out process or not, we are not going to anyway commercialize this, might as well publish it. So there are some research papers also which contain some of this data in terms of some of the top performing fibers.
Just kind of
So-
follow up on some of these. So
Oh yeah.
some of this is kind of, again, like proprietary. They don't really tell you much about it. But so it's, like I mentioned, it's kind of interesting how even when like, you look at one category, okay, we're focusing on stability design of these aluminum matrices, but they're all made of different core materials. So this touchstone material was a thermoplastic that was reinforced with aluminum, versus this Torica fiber was actually a high modulus carbon fiber. So again, when we looked at these, we noticed anytime carbon fiber was used, it was always high modulus carbon fiber, which is a lot stronger and kind of more advanced. It's kind of a basic carbon fiber you might
that's
use.
what depends upon the which precursor you use,
Yeah.
pitch or pan.
Yeah.
So one of them, I don't remember right offhand, gives you more strength but lesser stiffness. The other gives you more stiffness, lesser strength. So depending upon these specific application requirements, you choose one precursor over the other. So though at the end of the day they're both called, in a generic sense, carbon fibers, they have specific nature because of the precursor and the manufacturing.
Yeah, and so it kind of makes sense like when we go back to those equations, like if we're using high modulus carbon, then like if we're looking at buckling or stability design or stiffness design, if we're having higher modulus, of course that's going to be advantageous for like, if we're looking for a material that makes the most sense for those.
Yep.
Then one material kind of reminded me, I forgot what it was called, for this Supremex material, and for a lot of the other ones we looked at, it was a silicon carbide base. It wasn't a material I'd heard of before, but it was pretty consistently used throughout a lot of these. It's kind of like the base kind of the composite itself.
Yeah. Remember the containment that we talked about? There again, silicon carbide is something which is used, not for the containment, but more for the some of the engine components which have higher temperature requirements. So you typically use with a titanium, aluminum, vanadium alloy as the matrix. You will typically use silicon carbide fibers.
I just wanted to mention that this table is like moved for some reason. Like when we look at it on this thing, it's fine, but so you know all the data is there. Why did it move like that? Whatever. The data is there. Like it's not like we cut some data out. Like it's all there. So if you just want to look at the data yourself, like that's it's all like all the information is there. It just moved, so it doesn't look like it's there.
Right.
I just wanted to mention that. I don't think it really matters now.
Yeah.
One thing too that it factored into the design is density value. For like you see the densities in the equation, but to even just think about like the trade-offs between like the strength, but also like the weight stuff. Like some of these like might be stronger, but you can see like this thermal ceramics versus this Torica material. It's like almost double in density. So you might say, okay, this is like a better material, but if we can use this and it's almost as strong, but it's like half the density and lead like half the amount of weight, that can be huge. Like maybe you're willing to make that trade. So that's something we wanted to kind of talk about too, is it's hard to find cost necessarily, like whether or not it's worth adding that extra cost. But I think the one thing you can see is the density and the weights of, so a lot of times, like I mentioned before, you have these higher strength materials, but they weigh more. So maybe you just don't use them because sure it's a little bit stronger, but we'd rather just save all that weight. Or like maybe like in some of these, like we saw in the first presentation today with that diagram with the plane, like maybe you use it, but you're only using it very sparingly. Like you said, like in the engines, like maybe you're only using it there because it adds, you know, a lot more weight, but that's where you really need that more strength versus maybe, I said, especially in an interior cabin, you're not going to use something that's super strong. You don't need to be that strong. You can save a lot of weight. Or even like in the body and the fuselage, like you want something strong, but maybe like you do the math and it's not worth doubling your weight of that component to add, you know, that much more strength.
You really wanted to talk about cost. I think if we were to take this to the next level, we were talking about cost.
Sure,
Next.
absolutely,
Yeah.
absolutely, yeah.
But problem with the cost, like one of them we found the cost, but most of them was like, please contact our distributor.
Yeah.
And we'll get back to you with
Once
cost.
you buy it in bulk, or like they're selling it like hockey ball.
Right.
It's like kids, you know, so they're gonna tell us
Yeah.
the price yet.
I'm glad as engineers you're talking about non-technical stuff like cost, because that's something engineers have tended to ignore for a while, but I think that's very, very important. Sometimes you might be able to afford the cost, but it's also in terms of availability. See, for example, you mentioned silicon carbide fiber. It's made by just a few companies in Japan and
It's always
France.
like same from like the same couple companies would always make
Exactly,
silicon carbide.
exactly, because they have patented and they have the intellectual property for that. So they may not make it available to all countries, only those countries which they think are friendly to them, because especially if it's like defense applications
Yeah,
are
definitely.
involved and things like that. So the geopolitics also plays, so not only economics. Yeah.
Anything else? I think that's all we have.
That's it. Good. Yeah. Thank you.
Thank you.
How would we fare compared to the last class?
Much, much better. Yeah. Yeah. Much better. Yeah. I really liked it.
Do you think there's like a reason why companies tend to be focusing like these new materials on just, I said that we just look at like aircraft or some of the aircraft why it's always like long haul aircraft. Do you think it's just because like that's like your flagship and just trying it out there? Do you think it's just because of that like cost factor, like the cost?
Come again.
Do you think so? Like, you know, if you look at like Airbus and Boeing, like the places they're putting
Yeah.
all their like advanced composite materials is like only on like their long haul flagship aircraft. Do you think it's because like it's new to try it one thing at a time, or if it's just because like that cost benefit like you talked about only makes sense for like long range?
Some of the reasons you gave are valid as well, but the more important reason is in terms of the certification. So certifying agencies are really, really strict about allowing any new materials unless they are tested for a very wide range of specifications which they provide. And these tests are both theoretical, computational as well as experimental, and also flight tests on the actual prototypes. So only when they are satisfied in terms of the repeatability of some of these experiments, they will let the companies like OEMs like Airbus or Boeing use them, which is why you see a huge lag between the material being discovered or proven even in
these composites themselves like aren't new. They've been around like most of them like a long time. Like carbon fiber and like all these composites, like, they're not new, but it seems like just
absolutely,
pretty
yeah.
recently you're
True,
actually starting
true.
to use them in
True,
aircraft.
true. So the biggest stumbling block is the certifying agencies like FAA or whatever, and for the right reason, because safety is our topmost priority. So even though something might be guaranteeing very good performance, as long as you're not absolutely sure about the safety, the certifying agencies will not allow it. Very conservative.
Yes, that's
Yeah.
sandwich composites.
Yeah.
If we use that aluminium plates
Uh-huh.
with carbon fiber,
Uh.
how would that the strength between that carbon fiber and the aluminium sheets?
How the strength is?
Bond strength.
Yeah, with the
We are
bond
using
strength, yeah.
epoxy.
Yeah, so always the chain is as strong as its weakest link, right? So you have to really ensure the appropriate kind of bonding. So what typically people can do is to have grooves into which this bond happens. So see the whole thing about adhesive research is in terms of not only different materials for the adhesive, but also in terms of the actual way in which the overlap happens between the adherents. So there's a lot of technology in terms of the geometry that goes into that bonding. But debonding between phase sheets and the core, whether it is foam based or aluminum honeycomb or whatever the foam might be, whatever the core might be, is always one of the most critical things. And many a times in the past it's happened that you have really strong and stiff phase sheets, you have really good shear properties for the core, but just because of the interface not being interfacial strengths being low, you have tend to ignore those kinds of materials. So it's just like the fiber matrix combinations, they looked at epoxy as well as aluminum. Not all fibers are applicable for both. So the compatibility, the chemical compatibility is important. Same thing with the phase sheet and the core as well. So a lot of compatibility issues have to be taken care of. It's not just like you can just mix and match anything with anything. Okay. So we in yesterday's class we covered in detail the plane stress state. We showed the dangers of making that particular assumption. So what are the main issues? I talked about 3 of them. One is the boundary conditions are violated, especially for aerospace kind of boundary conditions where you have a pressure field and a shear field in the boundary layer, that's not taken care of. Secondly, you have the compatibility violation, that is the strain compatibility when expressed in terms of the stresses, it goes for a toss. Similarly, you look at the main mode of failure of many of these composites, which is in delamination, that cannot be accounted for as well. So all these 3 are major issues, but that's not the only 3. Just for I'm talking of only the biggest issues or stumbling blocks, but there are many more problems with this particular thing. There's also an equivalent approximation that or alternate approximation I should say, which is the plane strain state, which is assumed in some places where the gamma I3s are taken to be 0, whereas in this case the plane stress state, the gamma I3s are non-zero in general. So that's something that you need to keep in mind, because that can completely alter the overall model, whether it's plane stress or plane strain. One common area where plane strain is used is in civilian applications for dam constructions, where the overall length of the dam is maintained a constant, and therefore you can think of that direction of the length of the dam to be the third direction. And so essentially, just like plane stress state is valid or tends to be valid when you have thinner and thinner structures, there it is valid when you have thicker and thicker structures, like the dam's length. If you think of that as the thickness, it's very large and it doesn't hardly change. It hardly changes in terms of the overall length, even with the water being resisted, the flow of water being resisted from the river by the dam. So those are situations there. So very rarely you will find a plane strain state in many of the typical transportation vehicles. It's not that it's not there at all. There are very few. The more common one is the plane stress state, because of our lightweighting requirements in transportation, especially in aerospace, and therefore the kind of loads that are there. Like, even though we talked about the pressure on this, and therefore that's sigma 3,3 because the thickness direction is 3,3 and the boundary condition is not satisfied, but actually that pressure, the way, remember, these 4 edges are attached. If this is a panel of a wing, so it's, let's say it's this is along the span and this is along the chord. So this is just one panel that you take out, and if you look at that, there is an attachment at each of those 4 edges, as I showed in the on the iPad when I was writing out. So if this is the span, then you will have a transverse rib coming over here. You will have another transverse rib coming over here, and then you will have let's say a spar over here if it's let's say the leading edge spar, and then you would have stringer coming over there. So, and typically these are either riveted or bolted or adhesively bonded or combination thereof, in which case it pretty much acts like a simply supported kind of a plate. And when you have a situation like that, the pressure distribution on the top is of course causing a sigma 33. You can see that on the boundary condition on the top itself. But the more important critical load that causes is because if you can think of this phase on which I am applying a pressure, there is of course a resistance sigma 33, which is like a Newton's third law. But because of the way it is restrained at the edges, there is also a bending, because these edges are not allowed to move relative to those joints. So essentially what happens when I apply a pressure is this tends to curve in, right, which means it's bending. So there is a bending stress which is generated because of that. So this is sigma 33. There is, because of the bending that is going to happen in this way, there is a sigma 11 which is generated. Similarly, along the drag direction, which is along the aircraft's forward direction, there is again a bending that is coming out of that, and that because of that there is a stress sigma 22, which is why you see these this top layer is very good at taking the sigma 22, whereas the bottom layer is very good at taking sigma 11. And both of these sigma 11 and sigma 22 are much larger than sigma 33 itself. Even though the sigma 33 is directly related to the pressure that is applied, this will be of the order of, let's say, if the length is about L and the height is about H, L by H will be of the order of 10 or more, right? So that factor gets multiplied on sigma 33 to give you your sigma 11 or sigma 22. So for most of the critical first cut analysis, preliminary analysis or preliminary design, you may not even take into account those sigma 33, and there sigma 11 and sigma 22 are the determining factors. In addition, of course, because all these four edges are hinged through the transverse ribs and the spar and the stringer, what also happens is not only a bending moment diagram, but also a shear force diagram can be obtained out of this, because of which there is a resistance through shear at any given cross section. So that transverse shear stress is also something that needs to be accounted for. Again, that is something that is relatively small. Now, because that sigma 33 and transverse shear stress are small compared to your sigma 11 and sigma 22, the bending or flexural stresses, therefore your plane stress state is something that people tend to fall upon, which is fine. But if you're looking at the approximation for plane stress, all that it's saying is that the sigma I3 equal to 0, which is the danger zone we've talked about, because it cannot satisfy compatibility, boundary conditions, and analyze delaminations. But in reality, what happens is this is not after all so wrong, because these sigma I3, which are three stresses, 1, 3, 2, 3 and 3, 3, that is 2 transverse shear and 1 transverse normal, are actually fairly small compared to the remaining stresses sigma alpha beta, which includes 2 normal stresses, sigma 11 and sigma 22, which is what I just talked about as the flexural stress that is coming because of the bending in both the span-wise and chord-wise directions. It is bending. That sigma 11 and sigma 22, I told you, is of the order of, let's say, about L by H times that. And this is something that we saw even in the case of the fuselage, which is of a passenger aircraft. If there's internal pressurization, we saw that the pressure in you remember in an earlier class we talked about this. If there is an internal pressure P and we take this radial direction R as 3 x3, then you see in the same sense, because it's thin in that direction, because it's a very thin-walled cylinder that the fuselage is, the main stress that is going to come is a hoop stress. If you cut through it, and if the pressure is P and let's say the radius of this cylinder is R, then that's going to be that hoop stress that is going to be there. If let's say this is the R direction, this is the theta direction, which I'll call it as x2, and x1 of course is along the length of this whole thing. So in the coordinate system that we have, this is outward r, then essentially your x1 is going inwards, right? So this is your x1, or what you call as the z coordinate, typically in a cylindrical coordinate system where you have r, theta, z, right? Instead we are having the x1, x2, x3 system over here. So now once again I'm using this because to be consistent with the sigma I3 over here, I'm giving you your x1, x2, x3 analogy. So in the x3 direction it is very thin, which is what we are talking about over here also. X3 direction it is very thin, and you see that that particular hoop stress therefore is in the tangential direction, which is the theta direction, which is sigma theta theta, or I can talk about of it, if it's a curvilinear coordinate system of x2, I can talk of it as sigma 2 2, right? Sigma 2 2 or sigma theta theta is PR by T. So in other words, it's a thin walled cylinder. R by T is like a huge amplifying factor because the radius of the fuselage is very large compared to the skin thickness of the fuselage. So this factor R by T is amplifying P, whereas your maximum pressure that is going to come is because at the inner boundaries of this skin, which is equal to P. So at this location you will have your sigma 33, which is nothing but sigma RR is equal to P, because that's the boundary condition. So one of them, which is sigma 33, is P, which is order of P. This is of the order of PR by T. Order of magnitude is PR by T, right? So you see that amplifying factor, which is why I'm saying that sigma alpha beta is much larger compared to sigma I3. So this, whether it is in the case of bending and shear that we are talking about, where the transverse shear is also contained in this, remember your sigma 13 and sigma 23, which are nothing but tau 13 and tau 23, those are the transverse shear stresses. They are small compared to the bending stresses. Okay, so so in this case, of course, we were talking about sigma 33 compared to sigma 22. This is the case where internal pressurization is there in the case of the fuselage. The same thing holds even in the case of wing panel, where there's no internal pressurization, but essentially the outer pressure that is there is causing a bending, and that bending is going to result primarily in your sigma 11 and sigma 22 being much larger compared to your sigma 33, which is of the order of the pressure once again, which is the external pressure, atmospheric pressure, now not the internal pressurization that is there, which I can call as PI over here, whereas that is the external atmospheric pressure, or P at ATM. Okay, so that that sigma 33 there would then be of the order of the atmospheric pressure, whereas the bending stresses will be much larger than that. They will be amplified by a factor of L by H. We will go into the actual details of how calculating those the stress expressions, and at that point we will know the order of magnitude of sigma 11 or sigma 22, and we will see that indeed it's much larger than the pressure of the that is coming from the atmosphere. It's like this, just like your tabletop that you see over here. When you have all these laptops, water bottles and things like that, they're essentially creating stress in the third direction, which is the thickness direction of this tabletop. But that stress is very small compared to the bending that it is undergoing because of these loads, because it's attached, remember, at its legs, which are at certain frequency. You have the pitch of this table legs, and these are where the supporting is, and all of this weight will get added up and distributed between these how many were legs, 4 legs that it has. Then you essentially see that's like a bending kind of a deformation it's going to have, and therefore there is going to be, along the length of this tabletop, there's going to be a sigma 11. Similarly, along the width there is going to be a sigma 22, and that sigma 11 and sigma 22 will be much larger than the sigma 33, which is coming as a boundary condition wherever these loads are actually placed, wherever a mobile phone or a laptop is placed. That at that location alone there is a sigma 33, right? Whereas sigma 11 and 22 are present throughout the length and the breadth of this. Of course, they are not there at the neutral axis, which is the middle of this typically, but over, above and below there is essentially a compression on the top and a tension at the bottom, The more important point is their magnitudes, irrespective of whether they're compression or tension, as long as you take their magnitude. So what we are really interested in is not the algebraic value, but we are talking about the magnitudes over here. Okay, so same thing over here also, we are essentially talking about the magnitudes and comparing them and see that that relation holds good, that it is much lesser than. So same thing over here also, we are talking of essentially the magnitudes of these. Okay, is this clear from the plane stress point of view? Yeah. Okay, so one more thing that this plane stress will help you, as we already just briefly mentioned towards the end of yesterday's class. Now, all that it is saying is sigma, the plane stress problem is saying that sigma I3 equal to 0, which means these three, the third, fourth and fifth, go to 0, right? But then that results in a set of three simultaneous equations that you can have in terms of the corresponding gamma I3s. So here you have the three normal strains, followed by the shear strains, of which now these three quantities, remember in a plane strain problem they would go to 0, but here we are not introducing plane strain approximation but a plane stress approximation, in which case it's only the stresses which go to 0 and all the stresses are within the 1-2 plane, x1, x2 plane. That's why you have only sigma 1, 1, sigma 2, 2 and tau 1, 2, which can be in general non-zero. But here in general, for a generally orthotropic composite in particular, you can have all 6 of them non-zero in spite of plane stress over there. So that's something that you have to keep in mind. But in the case of the specially orthotropic material, where you have introduced the coordinate system parallel to the fiber and perpendicular to the fiber, there is some simplification you can get from this point of view also. So let's just look at what that is. So here it's a stiffness which is represented by C, which is actually a fourth order tensor, but we can take it using the Voigt notation as this. So next you have your C22, and from transverse isotropy we showed that C33 is also C22. So I will take advantage of that now and just put that also as C22. And then we had C44, which in your next homework you are already, which I gave to you yesterday, you're going to prove that that is equal to C22 minus C23 divided by 2. Okay, and then there is a C55, which is equal to C66, and therefore I'll write both of them as C55. Okay, so this is something that we already looked at in yesterday's virtual class. So you see that over there. Again, coming over here, you had C12, and because 2 and 3 are interchangeable, I can write C13 as C12 itself. Okay, so that those two are equal as well. Okay, on the other hand, this is different. C23 is different because it's the transverse Poisson's coupling between T and T prime directions, right? So this is all that we have, and the rest are all zeros, right? I'm writing it out explicitly instead of a single zero because we will use this to create those simultaneous equations. Okay, now we have these 3 as zeros, which means those 3 rows can be used to generate equations in terms of your gamma 33, gamma 23 and gamma 31, and you can actually solve that. And for this this is specially orthotropic. Which means it's a composite with the axis parallel or perpendicular to fiber direction, which we call as the longitudinal direction L or x1, right? So on the other hand, for any generic composite which has fibers in any arbitrary direction, like you see in the middle layers over here, second and third, which approximately are plus or minus 45 in this picture, but any other theta angles that you might have, which is neither 0 nor 90 degrees, then all of these zeros will vanish. But you will still have everything in terms of these parameters. And remember how many parameters we have? C11, C22, then we have C23, C12, 4 of them, and C55, 5 of them. So totally only 5 independent coefficients are there in this matrix as you see it, right? So in terms of those, even if it's not the axes are not defined as parallel or perpendicular to fiber direction, the structural axes are making, in this case, plus or minus 45 degree with respect to those 2 layers. Even in such situations, it will depend only on those 5 plus that angle theta. So cosines and sines of that angle will come into populating this, and in general you will have a fully populated 6 by 6 matrix of 36 coefficients, and that's what you have to deal with, right? So that being the case, now coming to in this special case, you can see, for example, if you take the gamma 23 and gamma 31, the matrix is diagonal on those 2 terms, right? Which means that if tau 23 is 0, then automatically you get gamma 23 also 0. And similarly, if tau 31 is 0, because of the plane stress approximation, this is plane stress. In reality, it is small compared to sigma alpha beta, not exactly 0, right? So you see that these 2 directly go to 0 because those are diagonal terms. On the other hand, gamma 33, even though it's equal to 0 over here, it will become a function of gamma 11 and gamma 22, right? So if you can explicitly write down that particular equation of the third row, you will see that it is C12 times gamma 11 plus C23 times gamma 22 plus C22 times gamma 33, and on the left hand side it's equal to sigma 33 equal to 0. Therefore this is equal to 0, right? So in other words, you are able to solve for gamma 33 as minus 1 by C22 times minus 1 by C22 times C12 gamma 11 plus C23 gamma 22. Okay, this is for the specially orthotropic case. Even in the generally orthotropic case, and of course the other 2 are 0. In the specially orthotropic case, these 2 are zeros. Why? It becomes just 0 divided by C22 minus C23 by 2 and 0 divided by C55. So therefore those 2 are zeros. Okay, this is only for the case that you have here. But as I said, in the generally orthotropic case, you have a fully populated six by 6 C, which means all the 36 coefficients will be non-zero in general. So when you have a situation like that, then you see that you can actually solve that those 3 rows become simultaneous equations. Okay, you will still have these zeros, you will still have all the elements of this, and then you can solve in terms of that. All of them will be functions of these 5 coefficients, independent coefficients, plus the angle theta of the fiber in that particular ply, and that can actually be solved, and then you can get the gammas which are in the third direction in terms of those which are in the in plane direction. So in other words, when you actually solve this, solve the simultaneous equations, linear equations, corresponding to the third, fourth, and fifth rows of C. So when you do that, all you will end up with is the 3 out of plane stresses or transverse stresses as functions of the in plane stresses. So once again, remember, whenever we use Greek, we mean that it takes on only the values 1 and 2. So it involves gamma 1 1, gamma 2 2, and 2 gamma 1 2, which are what are left over here, and I takes on the values all 3 1 2 3. Okay, so it includes then transverse normal gamma 3 3 and the 2 transverse shear, which is gamma 2 gamma 1 3 and 2 gamma 2 3. Right. A special case of that is this, because this is generally orthotropic, this is specially orthotropic. Okay, so both are composite, just that the way you place the fibers with respect to the structural axis is different. 2 special cases where it is 0 or 90, then you get this solution. If it is any other angle, you will get this solution, but you can use this solution in order to generate that also. So this is the more general solution that you will have. So it will be a linear function. This particular function is a linear function of the gamma alpha betas, which will be in terms of all those C's and the cosines and sines of the theta angle in that particular ply, in whichever you want to get this mesomechanic model in place. Okay, so is this clear so far? Yeah. Okay, so this is the advantage that you get, because once you are able to solve for gamma I3, I can go ahead and substitute for these 3 guys in terms of gamma 1 1, gamma 2 2, and gamma 1 2, and I can reshuffle this matrix and write it as just a 3 by 3 matrix multiplying only gamma 1 1, gamma 2 2, and gamma 1 2, because now these 3 are also functions of only those 3, right? So I can rewrite this whole matrix now as sigma 1 1, sigma 2 2, and tau 1 2, only the in plane stresses, because the others are anyway 0, and you end up with a matrix which is C11 bar, C22 bar, C33 bar, C12 bar, and for specially orthotropic this will go to 0, but I'll write it any case over here. So this is usually written as, to be consistent with that it's the 6th row, instead of C33 we put it as C66, okay, to mention the parentage or the source from which it has come. Okay, so once again this will be C16 bar, C26 bar, and this will be symmetric, and this will be related to the corresponding in plane strains, which are gamma 1 1, gamma 2 2, and 2 gamma 1 2, the 2 factor, making it an engineering shear strain instead of a tensorial shear strain. So this is the huge advantage that you're getting in terms of this particular approximation, which is why people tend to make it, even though it is not relevant. So the answer to this is it's irrelevant. So it's no, this assumption is not relevant, which is why we have it in the red font. But people who want a simplified model and are okay with a very crude approximate solution, therefore they think of it as a necessity to simplify their life in terms of the overall application. But with the kind of computational resources that we have, this is absolutely unnecessary. Without making that approximation, we can get really excellent models which are not only accurate but also efficient, computationally efficient also. So the argument that was there earlier that this is going to result in computational efficiency because it's just a 3 by 3 matrix is no longer something that we can buy, because even without making this particular assumption, we can get to a not only accurate but also efficient model. When accuracy and efficiency come together, it's essentially reliability. So you have a much more reliable model, because if it's very accurate model but inefficient, takes days on end to run on your computer for a simple problem, it's not going to be of much use. Similarly, if it runs in a jiffy, it just gives you the result immediately, maybe not even need a computer, a calculator, or even hand calculation is good enough, but the accuracy goes for a toss. So again, it's of not much use. You're going to end up with numbers which you can't use for any future purposes. So you have to have both of these. And whenever you try to increase the accuracy, what happens? The efficiency comes down. Whenever you try to increase the efficiency, the accuracy comes down. So you have to play a game in which you are trying to say, this particular thing is important for me. I want it to be this level of accuracy. I want to get all my errors less than 1% or 0.1%, let's say. Then I try to use a mathematical technique which can maximize my efficiency. So I keep one of them, the accuracy, as my benchmark, and try to maximize the other, which is the efficiency. So that is possible, and that is the current state of the art in structural analysis, and which is what we will venture into on Monday's class. So far, so good. So now, in lieu of your final exam, I said right at the beginning of the semester, I had shared with you a particular document. Okay, so some of you might have gone through it. Now I just want you to go through that. We have not discussed that in class, but I want you to just go through the corresponding video for the previous batch, and just you'll see exactly what I have done in that exercise. We have asked a few questions and we have tried to answer them using inputs from the students, which is what I planned to do, but we just ran out of time because the way this is structured with just 5 weeks with 8 hours left the next, I can't do that. So, but I want you to get lead time in terms of because it's the most important homework that you're going to solve. It's a take-home final, right? So I really want you to go through that particular video. In that itself, I've given the links to that video as well, so you can easily figure it out. So just go through that exercise and see how you can probably populate that. So coming up with what is known as a big canvas of structural analysis. So on one chart, you have all the variables, all constants that you have dealt with in all of your previous courses involving structures, namely your deformable bodies, your dynamics, statics, and maybe even high school physics. A lot of the concepts that you have learned, it can all be put up on that single chart, and then you will see the correlation between them. Once you have that big picture in the mind, all of structural analysis, even more complicated grad level courses, becomes a child's play. This is what I have seen not only from my own experience but from the experience of many of my students, and some of my students have gone on to become professors around the world, and they continue to teach this particular methodology that I introduced, and they say that even their students are immensely benefiting from that. So I know it's a tough week for you because many of the other things are coming up as well, but at the same time I would really urge you to spend quality time on this, where you can really focus and see what is the takeaway from that, and see how that can be translated to your own final exam, which will be due next Thursday. So you'll be making a presentation next Thursday related to that. Of course, on Monday I'll be talking about it in a little more detail in the class itself, but I just wanted to get you the lead time, because otherwise it will become from Monday to Thursday just 3 days. I didn't want that to happen, which is why I urged you to watch the video. Not that we're not going to do that exercise, we will do that exercise, but we'll do it in a way that you'll already be familiar with what that exercise is by watching those videos. Okay.
So that is the last one, that's the next one, is the last one?
Yeah, next week is the last week for this course, and Thursday will be the final homework, which is also a takeaway final, yeah.
There's nothing else.
Nothing else, yeah.
I guess we still need to finish the derivation. Let's see I don't think
You could do a derivation for C4 where it's equal to
Yeah.
C2 minus C2.
Correct. So that still remains, yeah. I gave it yesterday, yeah. So you can present that maybe Wednesday or along with your finals, however you wish.
I'm sure the same calculus.
Yeah. Okay. That'll be good. Yeah. Thank you.
So, for the final, is it like
Yeah.
a single page, just like an overview of everything you learned? We put it into like 7 columns, is that right?
That's correct.